So, you probably use stuff like ChatGPT all the time, right? But have you ever stopped to think about what's really going on under the hood? How does it actually understand what you're asking and come up with language that feels so human? Well, today we're going to peek inside the machine and see how these large language models actually work. Okay, so what's the big deal? What's the real difference between a regular old language model and a large language model? As you might have guessed, it all comes down to one thing, just absolutely mind-boggling scale. And believe me, when we say large, we mean it. The jump in scale is just wow. A few years back, a top model like BERT had about 330 million parameters. Think of those as the tiny learning dials inside the model. Now look at GPT-3 on the right, 175 times billion. That's not just a step up, it's like going from a go-kart to a rocket ship. We're playing a completely different game now. And here's where it gets really interesting. This isn't just about making the models bigger for the sake of it. Something incredible happens at this massive scale. It's like they suddenly wake up with new superpowers. Skills like complex reasoning that just weren't there in the smaller versions. Researchers have a cool name for this, emergent abilities. It's a case where sheer quantity creates a totally new kind of quality. All right, so how do you even begin to build one of these digital behemoths? Well, it all starts with something called the pre-training pipeline. Think of this as the boot camp, where the AI gets its basic training and forges its raw intelligence by just reading. And when we talk about the amount of reading it does, it's just staggering. Take this number, 2.6 trillion. That's how many text tokens, little pieces of words, a single model was fed. That's the equivalent of making it read a huge chunk of the entire public internet over and over again. But, you can't just dump the entire messy internet into the machine and hope for the best. No way. That data has to be cleaned meticulously. First, they filter out all the low-quality, toxic junk. Then, they deduplicate it to get rid of repetitive stuff that could skew its learning. And finally, the clean text is tokenized, broken down into numerical bits the computer can actually understand. It really comes down to that old saying, garbage in, garbage out. The researchers themselves put it perfectly. They say that training on a noisy, toxic, or repetitive set of data would largely hurt the performance of the models. The quality of the ingredients is every bit as crucial as the sheer amount. So what's the engine that powers this whole process? For pretty much all modern LLMs, it's a revolutionary design called the transformer architecture. Its real superpower is something called attention. Before this, models would get lost in long sentences, but attention lets the model pinpoint and weigh the most important words, no matter where they are. It's how they get that incredible grasp of context. Okay, so after all that pre-training, we've got a model that's basically a super intelligent brain in a jar. It knows a ton of stuff, but it's not very useful yet. It's more like a giant, disorganized encyclopedia. The next step, tuning, is where we shape that raw knowledge into something we can actually talk to, a helpful and safe conversational partner. The first phase of that is called instruction tuning, and it's pretty much what it sounds like. The model is given thousands and thousands of examples of instructions. Summarize this, write a poem about that, explain quantum physics like I'm 5 years old. This is literally how it learns to follow our directions. I love this analogy. It makes it so clear. Think of it this way. Pre-training is like a student spending years in a library reading every single book. Instruction tuning, that's like giving them a whole bunch of practice exams. It teaches them how to use all that knowledge to answer specific questions. Okay, but following instructions is one thing. How do you teach it something more human? Like how to be helpful or how to avoid saying harmful things? For that, you need the real secret sauce, a technique called reinforcement learning from human feedback, or RLHF for short. So here's how this RLHF loop works. First, you give the model a prompt, and it spits out a few different answers. Then, actual human beings look at those answers and rank them, from the best one to the worst one. All of that ranking data is then used to train a second model, called a reward model, whose only job is to learn what humans like. Finally, that reward model coaches the main LLM, nudging it to produce the kinds of answers that we, the humans, preferred. It's a constant cycle of refinement. All right, the heavy lifting is done. The model is built, trained, and tuned. Now, it's our turn. This is where we get to the art of the prompt, how we can tap into all that power. But that brings up a really mind-bending question, right? How can you teach a model something new, right now, on the fly, without going back and retraining the entire thing? The answer is another one of those wild emergent abilities we talked about, in-context learning. This is the almost magical ability of a huge model to learn a new task just from the examples you give it right there in the prompt. No new code, no retraining, it just learns. Let me show you what I mean. First up, we have a zero-shot prompt. It's called zero-shot because you give it 0 examples. It's just a straight-up command. You're counting on its pre-trained knowledge to figure it out. And for simple things, yeah, this works pretty well. But now, check this out. This is a few-shot prompt. See what we did there? We gave it just a couple of examples to show it the exact pattern we're looking for. By doing this, we dramatically boost the chances of getting the perfect answer. We're literally teaching it on the spot, just by talking to it. It's amazing. Now, as cool as all this is, let's be real. This technology is nowhere near perfect. And that brings us to our final section, a quick, honest look at the big challenges and what's next. First off, it's good to know that there are kind of two big camps in how these things are being built. On one side, you've got open source models, where the underlying code is public. Anyone can look at it and build on it. On the other side, you have closed source, proprietary models. They both have their pros and cons, and this debate is really shaping the future of AI. But whether a model is open or closed, nobody has cracked a few fundamental problems yet. The biggest one is probably hallucination. That's when the model just makes stuff up, but states it with complete confidence. The other huge one is knowledge recency. A model is basically frozen in time. It knows nothing about the world after its training data was collected. Solving these is a massive priority. And that really brings us full circle. We started this by talking about those surprising, emergent abilities that just appeared when the models got big enough. So as these things get even bigger, even more complex, you have to wonder, what other surprises are waiting for us? Are these the only emergent abilities we're going to see, or is there something else just around the corner?